Okay, welcome back to CE 528. Remember in the last class, we were talking about a bunch of different things. We talked about the internal rate of return, payback period as a measure for evaluating different projects. And then we also looked at how to do incremental benefit cost ratio analyses. And that's just basically, are you getting bang for your buck as you invest more money or invest more initial cost into your projects? So then we shifted over and talked about how if you have to do IRR, there might be some ambiguity, especially on projects that have both a high initial cost and a high closeout cost. And if that is the case, then you might have to resolve that ambiguity by taking care of closeout cost at a constant discount rate, distribute that over the analysis period, and then redo your IRR estimation. And then last thing we talked about was how the economic analysis, what is the meaning of R? We talked about how it's actually the opportunity cost of capital and not anything else. And then it's the real rate of return from the next best readily available use of capital instead of the investment being considered. And usually these types of rates are published by the federal agencies, such as the Office of Management and Budget. It's managed by the White House. It's a federal agency under the executive branch. So they publish this type of data and we just use them. And for the purposes of this class, I'm going to almost always give you that number, except when you're doing obviously IRR analysis, you won't use that number. You'll just evaluate the net present worth at different interest rate. So that's just in a nutshell what we talked about last time. I want to make sure that we just quickly go over that. So this is the new stuff. Like I want to wrap this up and then I will assign that lab for you. So the idea is of choice of economic lifetime N. Economic lifetime, which results in the greatest net present worth from holding the asset. So that's another way of looking at the project, because you might want to figure out at what point do you replace that asset? Like at what point a bridge should be replaced and what not. So what you're trying to find out is that at what point the greatest present worth is achieved. So instead of like having that N to put in your formula, now you're trying to solve for N. You're trying to solve for the capital N or the value of the asset for the net. So when you calculate net present worth, again, you do it over multiple periods of time, and then you figure out, okay, which gives me the maximum net present worth. So let's think about this through a cash flow diagram. And then N on this x-axis is the number of years that you'll have. And obviously you have a big cost at the beginning, and then you have a cost, but so first of all, let me ask you this. Looking at this chart, I hope you're all looking at this. Looking at this chart, my question is, I'm saying that this graph here, these purple bars represent cost, right? But I'm also telling you that there is a initial cost, which is below the axis, negative value cost. That's great. What about this number right here? How come there is a cost that's above the axis? What does that mean? You probably recall that discussion maybe from your 321, and that's my question for you. How come something that I'm identifying as a cost is showing up above the axis? You can again use either the chat or you can unmute yourself and speak. How is there a cost above the axis here? See something in the chat? That's good. A couple of messages, always like that. Oh, bunch of now. Yeah, so it's a salvage value. That's exactly right. And then this is again, this is really a salvage value. So I'm glad some of you remember it and were brave enough to note it in the chat. And I'm sure more of you remember it actually, but just didn't get the chance to note it. But if you didn't remember it, I'm just telling you right now that this is the salvage value that you might be able to sell some of these sort of used up assets at the end for some salvage value. And one thing about salvage value that you should always remember is that we should treat that as a negative cost. Okay? So salvage value should not be treated as a benefit. It should be treated as a negative cost. Okay. Now, if you remember, if you're doing benefit cost ratio, or whether you're doing net present worth, if you're doing net present worth, whether you treat the salvage value as benefit or cost, it wouldn't matter, right? Because it's just a subtraction or addition, and net present worth is just that. So whether you put it as a negative cost or a positive benefit, it's the same thing. However, it's important that you treat that as a cost, and it makes a difference when you're doing benefit cost analysis, because that's a ratio. So it matters whether or not you put the salvage value on the top as a cost, or subtract from the cost in the denominator, or add as a benefit. So that would make a difference, and your benefit cost ratio will be incorrect if you treat salvage value as a benefit. So I want to just quickly note that salvage is negative cost. Don't treat as benefit, okay? I just typed up that message in the chat. The salvage value is a negative cost. Don't treat that as a benefit. I cannot say this enough, so I'm going to type it one more time. So make sure that you remember that. And then the rest of this is just revenue here on the second chart. And these are the revenues. Revenues go up over time, but then at some point the revenues start to decline. And you can see that the third chart, the average annual operating and maintenance costs, they start out sort of low, but then they increase over time. And that's a typical sort of infrastructure project, right? I mean, it has some initial costs and some salvage, then it has some annual benefits, and then it has some operation and maintenance costs that start to go down over time, or that start to go up over time. And that's why, because as the asset gets older, it just requires more to maintain. So these are all the cash flow diagram on their nominal values in the year that the expenses or benefits occurred. Oops. And let me remove this annotation. So now what you do is you essentially figure out, as you vary the value of n, what is the net present worth as a function of n. Okay? So what I'm showing here, you here is a different sort of. So the blue line represents your investment, the initial investment. Why is initial investment line always a flat line? It's a very important question. If you understand all the things that we are talking about, all these different cash flow streams that we are talking about, it's very important for you to understand why the investment line is just a straight line. Just a straight line parallel to the x-axis. Why is that? It is a fixed cost, as someone said on the chat there. It is a fixed cost, but salvage is also a fixed cost, right? But if you look at the green line for salvage, that is not a straight line. That starts out the value, if you just have a 0-year value, but it starts to go down as n increases. So salvage value is also fixed, right? If you remember seeing that from the previous slide. Why is, as n goes up, and that's what's happening right now, and we're not varying interest rate. Remember, if you remember the IRR chart, you might be misled into thinking that I'm varying interest rate. No, my interest rate is fixed, or the discount rate is fixed right now. All I'm doing right now is I'm varying my n value, the economic lifetime. how come salvage value that's also a fixed value at the end of the cycle is changing as I change N, but my investment has a straight line? And if you feel like it's too much typing, feel free to unmute yourself and let me know. And I'm happy to pause the recording if that'll make you a little bit more at ease in responding. So I'm going to go ahead and resume recording. I'm just going to quickly, briefly say what I was trying to say. So net present worth of initial cost is always a flat line because it's always in the today's dollars. But salvage value, as you increase the lifetime, the salvage value is going to happen way into the future, and that's why it decreases in value. And all the other streams sort of start out small. The revenues start out small, they go up fast at the beginning, but then they flatline because the later cycle avenues are small. And then initially the operation maintenance costs start out small, but they go up. And as the N increases, they keep going up and up. And then this black line is just a summation of all of those points. And you're basically adding up all the different cash flow stream into the present value. And then this is where your optimum, so it starts out negative, goes into the positive territory. And then at the end, this is where you maximize the net present worth. Okay. And this N is also dependent on interest rate. So N value could change if you do this analysis at varying interest rate. So N could be different for 5% interest rate versus could be different at 2% interest rate and so forth. So that's always something that to keep in mind. But whatever interest rate analysis you have to do, that interest rate will be provided to you, even if there are multiple. So even if I ask you, find out optimum N, I'll give you 2 different interest rates, and then you could solve for it if you wanted. So any questions about this chart? Okay. So how do we compare between different values of N? So if there are alternatives that have different life cycles, N1, N2, etc. And this is something that we brought up very early in the game, very early in the class when we were talking about this. So there are some approaches that I outline here. So you could do this, compare over shortest NI value, ignore later effects. But that's a bad idea because in my 321 class, I always give an example of if you buy like a really beat up, really cheap car versus a little bit more expensive vehicle for transportation. If you just rely on this first method, you'll always end up the cheapest car possible without accounting for maybe more maintenance cost down the line. And then having to buy a new car sooner than you would like. Compare our shortest NI and then incorporate later effects through artificial salvage value. That's something you could do, but estimating salvage values could be tricky. You could explicitly augment project with short NIs with assumptions about replacement. So that's another way to do it. But the best way really is to replicate cash flow for alternatives for the least common multiple period spanning the entire period. So, and this is the best way to do it. And I'll illustrate that with an example right here. So, and this is the example. So this is the best approach this number 4 approach is the best one. You replicate the cash flow for alternatives to the least common multiple period spanning the same period or spanning the entire period. So this is the example of that. So let's say you have to compare projects between 10 and 15-year cycle, right? And you still want to estimate net present worth. So you basically, what you do is you replicate cost and benefit. What is the least common multiple of 10 and 15? It's 30, right? Because 10 times 3 is 30, 15 times 2 is 30. So if you figure out the LCM, least common multiple, that's 30. So then you basically assume that the first project goes on for 30 years. So basically, essentially replicate the 3 cash flow cycles every 10 years. And then for the second project, you replicate 2 cash flow cycles every 15 years. So you get like a 30-year period, and then you can perform your comparison as usual. There is actually an easier way to do this. instead of replicating all the streams and whatnot, there is actually a better way to do this that we learned in 321. And I don't put it here on purpose because I want to ask you if you guys remember that, folks remember that from CE 321. If you have two alternative life cycles, what else can you do that basically is replicating this solution that I'm outlining here? Any thoughts? Any thoughts on what can we do other than replicating these cash flow streams if we are comparing projects with different life cycles? I can pause recording, although I'll have to remember recording. So yes, that's right. What I've heard from the students is that just convert everything into an annual amount. So even if you convert everything to net present worth, just annualize that amount because we know the formula for present value given the annual value. Okay. What about n equal to infinity? What about n equal to infinity? So when n is infinity, that's basically a couple of assumptions that go with that. So anytime n tends to be like really, really large, like 50-year, 100-year, that kind of period, first of all, we neglect the salvage value because at that point, salvage value is something we don't worry about. We're not going to get anything. Even if we do get something, its present value, its real value for today's dollars would be essentially negligible. And remember, our uniform series present value factor is this one. But if you make n into infinity, basically what happens is that if you make n into infinity, this value becomes very, very large, right? So this value will become very large compared to 1. And then this is what it is. And then this will cancel with this one. If this goes away, so if this goes away, if n is very large, this goes away. And if this is away, then I could essentially cancel out this term with this term. And then I end up with 1 over I, right? I probably should be just drawing it. So if this goes away, this I can cancel out this. So as n tends to infinity, k becomes just 1 over I. So 1,000 per year will have an interest rate of 10%. It's essentially the present value would be $10,000, right? So that's sort of like, if you have n becoming exorbitantly large, this estimation is a good value to estimate. So even if it's a very large n value like 50 or 100 year, this approximation might be okay, might be acceptable alternative. Everybody can see how k goes to 1 over I. Okay. Very good. No questions here? So last concept I want to talk about here. The last concept I want to talk about is the capital budgeting. And capital budgeting is evaluation of engineering economics typically deals with choosing between mutually exclusive alternatives. But sometimes projects might not be mutually exclusive, right? So sometimes be dependent on contingent. So if you pick one path, that might preclude some paths, or it might open up some new paths. So there might be some dependent on contingent paths, and that's what we call capital budgeting problem. But we have a way of solving those types of problems. So, and then this could be dependent problem where the costs and benefits of alternative A change in the presence of alternative B. It could be contingent. In order to implement alternative A, it is first necessary to implement alternative B. So again, if you didn't do B, then you cannot do A at all. And then the cost and benefits of each alternative are unaffected by each other. So they might be like completely independent. So how do you do that? Basically, the idea is to kind of look at all the possible contingencies and dependencies between each other. And then you create all possible combinations of those. And then you could treat all those combinations as mutually exclusive, right? So you basically reduce that problem through enumerating all possible combinations. You reduce that problem as a problem that has those mutually exclusive alternatives. And there might be some combinations that won't work at all, and you can neglect them. And then there could be constraint optimization analysis that we are going to learn a little bit later in the class. We'll talk about that. So, but that's something, another approach that you take to solve the problem. But again, the idea is to look at all the possible combinations you have and what you can do and what you cannot do in the presence of another alternative. You just essentially list out all the possible combinations and then treat them as mutually exclusive combinations. Obviously, you'll have to take account the contingencies and dependencies. If you have varying timing for the projects, that means more alternatives there. And then if you run into financial issues, then you will want to squeeze all available money. I mean, you want to spend all available money by squeezing in less costly and less attractive projects. Again, you can run into that problem that we talked about, how the IRR values can bias you towards smaller projects. You might run into the same issue here. That could be avoided, but if incremental benefit cost benefit analysis is acceptable, then you could do that. But again, the bottom line idea that I want you to take from this capital budgeting framework is that take into account all contingencies and just do it by lining out or listing out all the possible alternatives. Now, that's a little bit beyond the scope of this class, so I'm not actually going to go and do this example for us. So we are not going to actually worry about this. But that's something that I want you to be aware of in case you ever run into it. Is all you have to do is write out all the alternatives. And then once you have a mutually exclusive list of all combinations, then you can go ahead and do your analysis like we have learned before. And then obviously all the things that we've talked about for mutually exclusive alternatives will come into play here as well. So make sure that you do that. And one thing, if you're interested in learning more about the benefit cost analysis, there is a Caltrans website, Caltrans maintained website that I want to show you. So I'm going to stop share and then new share. So this is a good one. And I think I talk about it in 322 as well. When should you use it? When you shouldn't use it? And then BCA versus economic impact analysis, perspective and scope, travel time, and how to do it for a project, value of travel time savings, vehicle cost, safety, emissions, induced travel, all those things. How do you account for that? This is a very, very useful portal if you ever have to do benefit cost analysis. And this is something that would come in handy for you when we do the next lab assignment, where we're going to do a little bit open-ended. So in the first lab assignment that I'm going to assign today, I'm going to directly give you the benefit, the cost, and everything for all the alternatives, okay? But in the next assignment, you're going to be writing out a build grant. And that build grant is essentially, how do you write that grant? And how do you actually estimate all this? So then that's where these things will come in handy, okay? And the last thing I want to do, obviously, is assign you a homework problem. It has two homework problems, 2 problems, and I'll post that on your Canvas page as well. So first one is pretty easy. Find the present value of series of payments, fairly simple. And then the next one is you have to essentially do a cost effectiveness analysis for the 5 alternatives. And then remember, so this is the second problem. The first one is a pretty easy one. You just have a compounding period. We did several examples like that in the class, in the notes here. But the second one is a combination of what you learned in lecture 1 and lecture 2. So read through it. If you have any questions, let me know. And this will be due on coming Tuesday before the class. So make sure that you submit it before the class next coming Tuesday. Okay. So I will post this homework problem. Are there any questions or anything like that? We'll go ahead and pause recording here.